Good afternoon, everyone, and welcome to the speaker series for the Center for Sustainability and Corporate Governance at IIM Ahmedabad. Today, we have the honor of hosting Dr. Professor Shreekant Gupta, and he has a long association with the Delhi School. Currently, he's with the Center for Social Economic Progress, Brookings India, erstwhile, and incredibly illustrious CV, which I won't go in greater depth. Today he's presenting a work in progress, and this is going to be in an area where a lot of our colleagues at IIMA are also interested, and it's gaining lot of attention, especially in the recent academic empirical research world. The impact of climate, changing climate, extreme climatic events on various sectors, industrial, agricultural, and so on and so forth. And this is a very interesting piece of work. Again, an applied econometric research works, empirical work, which tries to quantify the impact of disaggregated at a district level for India. So really looking forward to this talk, and moderating the talk we have colleague Professor Ram Mohan Turaga from the public systems group at IIMA. So what I will do is I would hand over the platform to Professor Turaga to start off with a small conversation with Professor Gupta, and then the platform is all yours. In terms of the housekeeping and logistics, we have audience in the room. We also have audience joining us live from Zoom. Over to you, Professor Turaga.
We'll start. We are already late. Thanks, Anish. Thank you, Shreekant, for coming here and presenting your work. So I don't know what my job is being a moderator, but I think, as he has already said, he will talk for about 40 minutes and present it, and at the end we will have Q&A. And because we have people on the Zoom, please use the mic when you ask questions, right? And
thank you. Yeah. Thank you. So thank you very much for coming, and for the CSCG to invite me. It's a great pleasure and honor to be here at IIM, and a really wonderful modern classroom. So today, I am going to be speaking about climate change and agriculture. This is a topic that has been quite intensively studied, but there are a few things that I think we can contribute. This is joint work with my co-authors, Professor Gaurav Dutt of Monash and Dr. Shweta Gupta of NCAR. So this is a work in progress in the sense that we are still refining the results even as we speak. But it would be very nice to get some feedback on this ongoing work. There is a very large literature on the impact of climate change on agriculture, as one can expect, given that agriculture is very directly impacted by climate change. And there are a very wide range of estimates of this. And I will make a distinction between climate and weather. So a lot of the current work really looks at the impact of weather variables, primarily rainfall and temperature, though you can think of other weather variables like humidity and various other things. There is a wide range of methodologies, different time periods and regions. The contribution that we are attempting to make in this literature is to try to show you that for very important reasons, some of these impacts hitherto may have been underestimated for various reasons. So as the title of our paper says, that is it possible that some of these impacts, significant as they are actually understated in the literature, are underestimated. This is just a snapshot of, there is a large number of studies. Most of these studies that I've mentioned here are for India, but there is a huge literature on the impact of climate change on agriculture. just jumping into our paper, what we have tried to argue in this paper is that there are three potential sources of underestimation of the impacts. The first one being that most models, almost the entire literature, is static models. That is, you have simply the contemporaneous effects in the sense of you do not take into account lags. So these are mostly contemporaneous or short-term effects, and they do not allow for persistence over time. Persistence meaning a shock in the previous year could sort of keep transmitting into the current year. So static panel data models do not capture persistence. If you capture persistence, you can parse the impact into a short-run and long-run impact. And therefore, if you do not look at the long-run impacts, you obviously end up underestimating the impacts. So that's essentially the idea. And the difference can be even an order of magnitude. So I will try to convince you that the long-run impacts are significantly higher than the short-run impacts, which do not allow for persistence. The second potential source of intra-year variability. That is, if we're looking at annual data, there are lots of variations within a year. And finally, the impacts can be asymmetric in the sense that, say, for example, a positive temperature shock versus a negative temperature shock. For example, a very hot year and a very cold year may have asymmetric impacts. It is not to say that the literature doesn't understand these things. There are papers that have looked at one of these. So, for example, there are a number of studies that have really looked at short run and long run. And Dell, Jones, and Olken is a very classic study that doesn't look at agriculture, but it really looks at persistence in climate shocks on economic growth. The paper by Wing et al. Does look at long run and short run impacts, but it doesn't do the other two things that I have showed you earlier, which is intra-year variability and the asymmetric impacts. Thirdly, you have some papers that look at within-year variability. There are some papers that look at nonlinearity. Our contention is that, or our contribution is that we are trying to address all three sources of potential underestimation in the climate impact. So basically, what we are trying to do in this paper is that we use a dynamic specification. It's a dynamic panel data model, which enables us to estimate the short-run and long-run impacts. We also look at intra-year variability by extending our baseline annual model into a seasonal model. So we try to look at seasonal variability. And then we also allow for asymmetric impacts in terms of positive and negative climate shocks. And we test all these econometrically to convince you that all these ways of modeling are statistically valid, so to speak. So that's the basic idea. Our data is also highly disaggregated. This data set is being widely used, but it is highly granular. And our data set covers almost the entire gross cropped area of the country. And the data set is fairly rich. It's about 50 years, so it's a very long panel. And that is also extremely important because climate change manifests itself in a very long-term manner. So it's important to not just look at shorter slices, but to look at as long a slice of time as possible. And in our case, the data we have on agriculture goes back to the 1960s. The climate data, of course, stretches even further than that, but for our purposes, we look at roughly about 50 years of data. We also look at all major crops in the country. So we look at food crops, cash crops, and this accounts for 95% of total output. So the study is as comprehensive as possible in terms of its coverage of the agricultural sector. And it's also as comprehensive as possible in terms of the time span and in terms of the granularity at the district level. What we don't have, obviously, is seasonal production data. We do have seasonal climate data, but I will come to that. This is work in progress in the sense that we are also now looking not only at the impact of climate change on yields, but we are also looking at the impact of climate change on acreage and on output. So yield, as we know, is a measure of the productivity of land, its output per hectare. You, of course, can have other measures of productivity as output per unit labor and so on. So we are extending this work, and we are also doing some projections that I will talk about momentarily. So just to set the stage, the Indian Met Department brings out an annual assessment of the state of climate. And as you can see here, these are what we call temperature anomalies. So these are deviations from some long run average. So what the Met Department does is it uses a 30-year long period average. It's a moving average. So they move this window. And as you can see from here, these red bars are negative anomalies, and those, these red bars below the zero axis are negative, and those are positive. This is not our data, this is the Met Department data, but I'm just showing it to you to give you a sense of how the climate in our country is evolving. As we know that India in 2024 is at least 1.2 degrees Celsius warmer at the beginning of the century. If you look at the planet as a whole, it is about 1.6 degrees warmer, but that is compared to pre-industrial. So we do not have climate data before 1901. But if you look at these headline numbers like 2 degrees, 1.5 degrees, those have a reference period from 1850 onwards. But let me just move on. We know that 2024 was the warmest year on record. So every year we sort of seem to be breaking temperature records. And as far as India is concerned, 2024 is the warmest year on record. The previous was 2016, and the 30-year long period average itself is sliding. So earlier they had a reference period of, say, 1980 to 2010, then it's 1990 to 2020. 10 of the 15 warmest years ever recorded in our country have been in the last 15-year period. That's 2010. And the past decade has been the warmest decade on record. So these are just some headline numbers to tell you how the country's climate is changing. This is rainfall, and these are rainfall anomalies. It's a busy chart, but what you can see is that on the whole, there's not such a clear pattern in rainfall as you see in temperature. But this is the Met data. I don't want to go too much into it. I want to talk about the data that we have used. So the data that we have used as far as our weather is concerned is gridded data from the Indian Meteorological Department. And the grids are essentially at 0.25 degree resolution for daily rainfall. And then we have daily temperature, min, max, and mean at 1 degree resolution. And this data, as I said, goes back quite a bit. But for our purposes, we use a 52-year data set for 663 districts. So for 663 districts, as per the 2011 census, we have this daily rainfall, daily temperature at the district level. So that's about almost like over 12 million observations. We've kind of aggregated them, and we have done two things. Firstly, we have apportioned these into ICRISAT districts. So the agricultural data basically comes from ICRISAT. And as you know, the number of districts in our country has kept increasing. So the original ICRISAT districts were about 311. So we have had to shoehorn back the climate data. So this involves two steps. First, you have the gridded data, which you convert into district boundaries. So you convert it into these districts at the 2011 census, and then you apportion it back into the ICRISAT districts. And we use this data to construct annual and seasonal rainfall for each district, which is the sum of daily rainfall. And we also use this data to construct annual and seasonal mean temperature for each district. So this is essentially what our climate data is about. Our agricultural data comes from the ICRISAT VDSA apportioned meso database. Some of you may have seen this database. This database is now been taken over by the Tata Cornell Institute. So it's called the TCI-DLD, the Tata Cornell Institute district level database. It's being widely used by people. This has district level data for 10 major crops. It has data on yield, on gross crop area, on production, and the data for other things like irrigation and fertilizer and HYV is not that complete, but there is a bunch of data out there. What we have done is that, for example, as I've already told you, the number of districts has increased with the subdivision of districts from about 311 in 1966, and at the moment we have about 780 districts. So in ICRISAT, there is this notion of apportioned and unapportioned data. Apportioned data simply means that, so the unapportioned data is the correct number of districts in any given year. The apportioned data uses the 1966 boundaries to apportion the data for the new districts back to the original 311 districts. This is quite important. So, for example, closer home to where I live, in the region of Delhi, there's a district called Ghaziabad, which got split into Gautam Budh Nagar and Ghaziabad. Sometimes the districts get kind of split, but that's the easy part. You can merge it back. So if you were going to construct an uninterrupted data series for Uttar Pradesh, you will simply put Uttarakhand back into UP. But sometimes that's not so simple, because what happens is that the child districts come from two separate parents. So in that case, you have to apportion it back and figure out how much of it came from a different district to put weights on it. So I'm just trying to tell you all this to give you a sense that this work is not trivial. So luckily for us, what happens is that the ICRISAT gives us two data sets, an apportioned and an unapportioned. The apportioned data set goes back to 1966. So it's referring to the district boundaries as it occurred. Of course, the size of the country doesn't change. It's just that the districts get fragmented. And what we do in our work is we do not look at all 311 districts. We look at a subset of those districts. So for example, if we simply look at 213 districts for rice, these account for 99% of the average output in our data set. So instead of then, looking at all 300 districts and 311 and adding noise to our estimation, what we do is these are the number of districts. So for example, 108 districts in the country account for 99% of cotton production. So that's what we are doing. So that's the data that we're using. And then to go back and tell you that, so this is it's a clean data set. It's a balanced panel with output and yield and acreage and so on for this entire period. And then just to go back and tell you, this part, we have these districts and we have had to shoehorn them back into those 311, so that now we have a data set with these 311 districts with outputs and yields and acreage and everything of all these crops. Plus we have this daily rainfall, daily temperature, which we have tried to use in our analysis. If there are any questions about the data, I can take them now, just to make sure that we've understood, though I suppose it's fairly evident. Okay. So this is essentially the entire coverage of the union of all the districts that we've looked at. Just a very quick note on climate and weather. Sometimes these are conflated, but weather is not climate. Weather is the realization of a particular draw from this distribution. So that is what is climate. That is what is weather. So climate, as many of you are more technical will know, it's a stochastic process. So it's a description. So the mean, normal temperature and so on. And so the whole idea why I'm trying to tell you this is that if you're only going to use daily rainfall or temperature, as several studies have done, you're really not picking up the change in the climate. So a climate change could be, so typically what happens in climate literature is that you have these normals. So typically you have a 30-year normal, like I showed you in the IMD data. It's a long period average. So you have these, so climate change is a change in the statistics of the process. So for example, you can have a change in the decadal temperature or a change in the long period average. So we are trying to make this distinction between climate change and changes in weather by actually looking at changes that are happening to the normals, so to speak. Okay, so just to make that more clear, what we do in this paper is we construct what are called standardized rainfall and temperature anomalies. So anomalies is the way climate scientists think about, and the graphs I was showing in the beginning are essentially anomalies. These are deviations from some norm. What we have done in our paper is that we have calculated these. So anomaly as is defined here is a deviation of current levels from some reference point, right? And that's how the WMO, the World Met Organization, also thinks about it. If you look at things like IPCC and all, they think along these lines. So what we do in our work is we create 30-year district-specific long period averages. Remember, our data is from 1966 to 2016, 17. So we take the first 30 years, and we've tried different periods. We take the first 30 years as what we call our LPA, and then we take the difference from that LPA and an actual given year, the difference in temperature and rainfall, and that is what we are calling an anomaly. And we standardize the anomaly to allow for comparison across by dividing it by the standard deviation. So we also calculate the standard deviation of that rainfall or temperature for that 30-year period, and then we use that to standardize. So what we ultimately end up are standardized rainfall and temperature anomalies for every year for every district. That's what we end up doing. So we allow, so when I talk to you about the three sources of potential underestimation, I said the responses can be nonlinear, which is what I said, asymmetric. So the asymmetric or nonlinearity is being allowed. So these are going to be key variables. So RIT plus is the rainfall anomaly in district I at time t. RIT minus is a negative anomaly. And basically how we define it is that rho IT is the rainfall in district I at time t. Tau IT is similarly for this. So we calculate the standardized anomaly and we use an indicator function. So we say that if the standardized anomaly, if it's only exceeds 0.1 or more, then we put it, otherwise we take it as 0. Okay, so we have a threshold. Now this threshold, we don't have to have it. We have tested the robustness of this without using a threshold. With a 0.2 threshold, it really doesn't make much difference. So our standardized anomalies are essentially this value will be this actual value if this deviation is more than 0.1. Okay. This is simply telling you what the data looks like. As you can see, that if we are looking at these long period averages across these districts, you can have a very dry district. This is obviously some place in Rajasthan. I think it's Bikaner, whose long period average rainfall is only 193 mm. And this 3600 is, I think, Jalpaiguri in Bengal, which has so much rainfall. Similarly, you have very cold, these are normals. So these are what we would call long period normals. So the long period normal temperature is about 18 degrees. I think this is in Kulu and this is somewhere in South India. I think it's Tirunelveli or one of those places. So this is just giving you a flavor for what the numbers look like. I don't know how much time I have. I don't want to go too much into the graph, but these are the graphs that we have calculated. And what you have here is basically, as you can see, these are the standardized rainfall anomalies. These are kernel density plots. And what you can see here is this is sort of the blue line is the first base year, and the red line is for the end. This is the beginning of a period, and this is the end of a period. And you can see a slight leftward shift in the rainfall. And here you can see a much marked shift to the left here and to the right here. So a couple of things that, without going into more detail in explaining this figure, couple of things that on the whole, things are getting warmer. And there is a somewhat discernible trend, downward trend in rainfall as well. And more importantly, what you can see by these kernel density plots is that you do have a distribution of negative and positive anomalies. So it's not simply that climate shocks have too much temperature, too high, but you can also have too low a temperature. So the climate shock in terms of too much rainfall, too little rainfall, that's kind of important. And we are trying to separate this out. And I believe that this paper is probably one of only two that has done it so far. This is not, how should I put it? This is an important idea, but it's there out there, but it hasn't been exploited in the work so far. And I'll also show you results which justify doing this by testing the equality of the coefficients. So it's not simply an assertion. I'm going to prove it to you. So very quickly then, these are trends in yield. Again, I can go into that. Let me jump into the econometrics of it. So the econometrics of it is also fairly straightforward. We are allowing for the persistence. We are allowing for persistence of two types. We're allowing for persistence in the climate shocks by taking anomalies and lagged anomalies. And we are also allowing for persistence in yields by taking lagged yields on the right-hand side. So we are allowing for all of this. So that's why we have this AD11 specification, 1 period lag of the dependent variable and 1 period lag of the climate variables. You can, of course, so this, sorry, question? Any question? Basically, what our specification is also doing is we're having asymmetric effects. We're allowing intra-year variability in the seasonal model. And then we also have a regional model to account for agroclimatic zones. I'm not going to show you the regional model. I'm going to briefly talk about the seasonal model. But our baseline model is an annual model. And in the annual model, we have lagged anomalies, lagged yields, and these are just 1 period lags. We tested, so we found that this specification worked the best. So why intuitively should lagged yields matter? Because as you can see, the shock can take time to work itself way through the system. Firstly, intuitively, if you think of climate shocks, a very dry year may reduce the groundwater levels. So it kind of persists. So it's quite easy to think about, lagged climate shocks. So what happened last year could be important for this year. Similarly, lagged yields are also important because the lagged yield, the yield last year, is a proxy for a number of things that are determining yields, right? So remember, a lag model also, the 1 year lag will also include the lags of that, right? So it's kind of recursive in that sense. But also econometrically, we find that lagged yields are an important predictor of current yield. I'll quickly go over. So I'll just try to tell you what's happening here. So in an AD11 model, you have, say, yield of district I at time t. This is the lag of that. This xit is a explanatory variable. In our cases, it is 4 of them. There's a positive temperature shock, a positive rainfall shock, and a negative rainfall shock. So xit represents that. And xit minus 1 is a 1 period lag. These are district fixed effects, and those are time fixed effects. So fairly standard AD11 specification. The AD11 specification, if you just go through, and this is very standard, econometrics, what really is important here is that using this, you can tease out 3 kinds of things. You can tease out the contemporaneous effect of the climate shock. You can tease out the short run effect, which is beta naught plus beta 1. Plus, you can work out the long run impact, which is essentially beta naught plus beta 1 divided by 1 minus alpha. So these are these 3 things we can recover from our data if we use an AD11 specification. So just to expand on this, just to expand, this was the simple one, this one. But if you want to write it out in its full-blown form, this is what our estimation looks like. So we have crop C, district I time T. So this is the lagged yield of crop C in district I time T. This is the positive rainfall shock. This is the negative rainfall shock. Similarly for temperature, and these are the lags of that, right? So these are explained here. And then, of course, we have district and time fixed effects. This again is a general specification. And what you do is in this general specification, you can have special cases. So for example, if you were looking at a partial adjustment model, it only looks at current contemporaneous values. So betas and gammas are all 0. If you look at a finite distributed lag, what you do is you set the lag values to 0. And then you have these leading indicators. So in the general specification, you can have special cases like this. Again, I didn't want to go into everything, but this is really the key slide where we show you what we do. So when we look at these beta naughts plus beta ones, we are getting the short run effects. The long run effects are given by this. And if you want, you can go back and work your way through it. Then you have the ratio of the long run to the short run. So that is fairly straightforward. The ratio of the long run to short run, you can take any of these. And so, for example, if you take the long run is here, and then if you divide it by this, you will simply be getting this, right? So 1 over 1 minus alpha is, that doesn't change with whichever coefficient looking at either beta or gamma. And what you can see here is that statistically, if this alpha lies between 0 and 1, then the ratio of the long run to the short run will be much higher. So that's all that we are trying to do. Now, this is, I asserted to you that persistence matters, lag yields matter, but ultimately it's an artifact of the data. It's the data that is telling us that. The data is giving us the alpha values. And from that, we are able to tell you convincingly that the ratio of the long run to the short run is going to be greater than 1, right? Okay. And I can go into this, but let me just first show you our one of our main results. So the main results is that if we're looking at the lag yields, those alphas, we find these alphas to be positive and significant. So what we argue is that there is clear evidence of persistence in crop yields, and the static specification is convincingly rejected. So it's not simply an assertion. It is, our data is telling us that lag yields matter, they're significant. And also, if you can look at this, all these numbers are essentially between 0 and 1. So if you put that in the denominator, then you find that the ratio of the long run to the short run will definitely be greater than 1. So that's something else that you may want to keep in mind. So all we are saying is the lag yields are all positive and significant, which means they should be there. And that's why I think the first and most important thing is that you must have dynamic panel data models to do this kind of work. In the literature as of now, there are maybe just a few papers that are doing this. Of course, there will be more literature out there, but this is where we are right now. Again, I don't want to show you too many things, but let me just show you just 1 or 2 of these. So this is a baseline model, and this is looking at the impacts of temperature across these 10 crops. So the positive short run is essentially going to be that beta naught plus beta 1, right? This is temperature, so there will be gamma naught plus gamma 1. And this is the negative, this is the, sorry, so this is the short run and this is the long run. So as you can see here, the short run coefficients are given by gamma naught plus gamma 1, and the long run coefficients are given by this number. And as you can see here, that what we have here is that all of these are mostly highly significant and negative. So this really means that the impacts of temperature on yields is negative and highly significant. And also you can see here that most of the long run coefficients are much bigger than the short run coefficients. Well, somewhat bigger. So I don't want to go into too much of this, but basically just to show you these two charts. In these, we are looking at the annual model. We are looking at the impact of these positive and negative rainfall and temperature shocks in the short run and the long run. And almost uniformly, we find them highly significant and negative. So these are just the plots of these. So these are the 95% confidence intervals. This is the estimated coefficient. And this really, all these graphs are essentially encapsulated in this. So I'm going to just skip through these and come to the sort of the headline, one of the headlines. So the headline is the ratio of long run to short run, which is 1 over 1 minus alpha. And what we can see here is that, for example, for rice, the long run effects are at least 36% higher. And this is easier to be seen in this picture here. So in this picture, the blue bars are the extent of by which the long run exceeds the short run. And those red lines are the confidence intervals. So this is our main finding, or one of our important findings, that because we are allowing for asymmetry, which in a way is also non-linearity, because we are allowing for persistence, we are getting impacts that are much higher than if you did not do this, right? The next thing and the last thing I'm going to, so anyway, this is simply trying to tell you that this is not simply an assertion. So we test for the equality of the coefficients, the beta plus, but the beta minus, and similarly for all of this. And we can see that we reject this null. We reject that these coefficients are equal. So therefore, we must bring in these separately. And this is also not very commonly done in the literature. In fact, it's hardly done, if at all. The second thing is, of course, now, just this, I'll be almost wrapping up now, if that's okay, or another 5 minutes. I told you there's also intra-year variability. Literature does pick that up, to be fair. Different people have tried many different things to pick up intra-year variability. What we have tried to do in this is we have looked at seasonal data. So we have looked at various ways of parsing the year, and we have come up with roughly 4 seasons. Remember that our left-hand side variable is annual. We do not have seasonal crop output at the district level. If you want seasonal output, say Rabi Kharif, then you have to go up to the state level. It may be available for a few states for a shorter time span, but if you really want to look at seasonal crops at the district level for all the crops, for all the years, it's not available, unfortunately. So what we have simply done is, instead of using one beta, now we have 4 of them. So we calculate the anomaly for season 1, season 2, season 3, season 4. So we, instead of having just 4 of these, now we will have 16 of these, right? So what we are simply doing is, on the right-hand side, we are introducing intra-year variability by calculating not just one annual anomaly, but we are calculating seasonal anomalies, both for rainfall and temperature, both positive and negative. And again, as in the previous interpretation, the short-run effects are simply the beta naught plus beta 1. And the long-run effect continues to be just that 1 over 1 minus alpha. So again, I can show you the results, but to convince you that disaggregation is important, we test for symmetric effects of positive, negative anomalies, current and lag, as we did earlier, and we reject. So we do argue that asymmetry matters. And so the null is rejected. And we also test whether the annual model is an acceptable restriction. And that again, we can test by looking at the equality of the parameters. And we reject the null. So we test whether the annual model is acceptable, and the test strongly reject the null. So what is the bottom line? The bottom line is that you must have positive and negative rainfall temperature shocks entering. The bottom line is you should have a dynamic specification. And the bottom line is that you should have intra-year variability and not just an annual model. So I think that's about it. These are some of our findings, which are mostly robust. So now we have a seasonal model. And here I'm not showing you the short run impacts because those will be too many. I'm simply showing you the long run impacts, which is that, the ratio is 1/1 minus. So maybe that I should have corrected. But so the long run effect is in the numerator, you have the beta or the gamma. And in the denominator, you have the 1/1 minus alpha. Okay. So that's what we have. So this is my last graphic. So, because this is a recursive model, you can actually try to calculate that this kind of persistence, how does it kind of wash out of the system? So what we are finding is that if you look at all our 10 crops, so this year is simply the contemporaneous effect, right? So when you look at the year one, this is just that beta naught plus beta one kind of idea. But if you look at it, you can see that the 80% of the long run impact is realized within 2 years and 90% within 3 years. And by 5 years, so if you have a one-time shock, then it kind of reaches back its sort of equilibrium state in about 5 years' time. So that's essentially it. There's a bunch of other stuff. This is projections. We are redoing this work. So what we did so all of this that I told you was historic, right? We looked at this data, we estimated these impacts. What is of greater interest is what's going to happen in the future. For that, we need climate projections. Now, climate projections are of different types, depending on what state of the world you imagine to be. So in the earlier IPCC, you were doing RCPs. Now you have these SSPs, the shared socioeconomic pathways. The problem again with this data is that this is highly aggregate. So to downscale that data into district level, and because we need it at that level of granularity, is not easy. We just managed to lay our hands on the absolute values of rainfall and temperature for every year from now until 2050. Earlier, we didn't have that. We simply had endpoints and a midpoint. So we interpolated to make these projections. So we are going to redo these projections. But essentially, what we are trying to show to you using our district level variables is which will be the highly impacted districts. But this will hopefully change. But in terms of policy, what's going to happen in the future? So that's what we're trying to share. Now, the caveat here, of course, is about adaptation. So anyway, to conclude, our main takeaways, I've already told you that we have a very, very significant impact. 1 sigma increase in these rainfall anomalies can have very major impacts on output. And also, for example, there's an earlier paper that says a 1 degree increase in temperature reduces yields by 2 to 4%. And we find a much higher impact, as I've tried to show to you. I think the last thing is that there is this whole issue about adaptation. What about adaptations? Well, in a way, as I understand it, since this is a panel, that's already built into it. But when you're doing the future projections, how are you going to think about adaptation? So that's something that is left open. And maybe if people have some thoughts on that, one can take it there. I hope I finished on time.
Thanks a lot, Shreekant. Questions?
First of all, thank you for such a wonderful presentation. My question is a basic question. If I understood it correct, there are 5 elements of weather or climate, 5 elements. Other than rainfall and temperature, there is pressure, there is wind, and there is humidity. Have you also explored those elements also in your calculations, or it is just temperature and rainfall?
No, we don't have data on that. If we had, we could try to bring them in. But particularly, I think humidity to some extent. But to get this granular data, so almost all research on this focuses on the key main variables, which are like rainfall and temperature. When you go to a doctor, you have many parameters the doctor can check. But the most important thing the doctor will check is your pulse and blood pressure, or maybe your temperature. Look, these are 2-3 headlines. But there are many other things. The doctor can check your cholesterol, XYZ. Those are important. But as a headline, I think temperature and rainfall capture the vast aspect of it. Not to say those other things are not important. Some people have looked at soil moisture. as important. Wind speed, yes, but we're talking of crops, so we don't know how relevant that may be. It could not. People have looked at nighttime temperature because rice matures during night. So not matures, but when rice is maturing, very high nighttime temperature can impact rice. So that can be picked up by looking at the maximum, right? So in a way, our positive temperature shock could be capturing that. So there are many different things in the literature in terms of that.
Hello, sir, and thank you for such a great presentation. So my question is that, as you mentioned that the entire thing that you did, your entire data things and even the climate, the future of that, using that data to predict the future implications of the climate. So I just wanted to know to what extent can this data be used by the central or the state governments in their policy formulations? For example, like in the MSP frameworks or like the Pradhan Mantri Fasal Bima Yojana, because I think at the ground level, taking a data-driven knowledge is a data-driven decision is much more important. But in the central government, what I could see is that most of the policy making is not very data-centric.
I cannot comment on policy making, but I can only say that this is a very good question. And ultimately, if this work has to be relevant, you would ask the question, so what, right? So the question is that, yes, so for example, and there's earlier work also, for instance, if you intuitively think that millets have less impacts, then that does, when you're talking about climate proofing agriculture, you may want to diversify crops. Again, this is not something that is entirely new. People do understand this. So when it comes to MSP, as the government is already now doing, it's extending the MSP to more crops other than rice and wheat. So that's common sense, but the data does back that up, you know. So this work, and then I have some other work where I have been looking at, I have 2 papers where I've simply looked at only 3 crops. Pearl millet, which is bajra, then there is jowar, which is, I think it's called sorghum, yeah. So I've looked at pearl millet, sorghum and rice, and basically, again, as one would expect, those crops show less impacts of climate shocks. So in a sense, that tells you that you must diversify. And one policy hook to help people diversify is MSPs, right?
I just asked that question because even now, sir, the crop risk and premium is not a part of the MSP framework as yet. And I have previously worked in the cooperative sector, so I am very well aware of the agricultural aspects of the thing. That's why I asked you the question.
No, that's a good question. And also in terms of the spatial impacts, when you show that, so Vidya is not here, but she's doing vulnerability at district level. So you can also from this, you know, in projection, if you can show which are the districts that are going to be more impacted or the states that are going to be more impacted, then definitely that's an important finding. And if one were to go further in the policy, we have what's called the Finance Commission, which does the vertical and horizontal devolution. And there are various formulae that are there. And for example, the 16th Finance Commission is finalizing its report. And of the last 2 or 3 finance commissions, they use some environmental criteria in it. For example, forest cover and so on. So if you have very hard numbers to show that these are the states that may be more impacted, not just in terms of agriculture, but there are ways to look at state GDP, then those could be then built into a finance commission. You could even think of something like an environmental finance commission because you want to have this devolution. So now that can be, rather than just having an ad hoc number, you can try to use this kind of analysis to inform a more scientific way of, or I don't know, a more systematic way of allocating funds across states. So that's a possibility.
Good evening, sir. Thank you for the wonderful presentation. I wanted to ask, you mentioned about laying hands over some granular level data, but for the methodology of the downscaling, were there any downscaling logics that you considered for the context of the granularity level of data, and or were some principles or considerations in terms of logics of the smaller scale level considered?
So if I've understood correctly, our binding constraint now is the agricultural data, which is only available at the district level. There is data at the, say, the taluka level, but in a few states. And there is always a trade-off. So for example, if I wanted seasonal output, I could have to go up to the state level, and if I wanted for the entire country. There are papers that have studied these kinds of things for smaller regions. So there is, say, for example, a paper that looks at Telangana alone, and it has much more, so you can get more fine-grained data, so to speak, right? But then you're only looking at one geography. And I must also say then that, you know, because there are literally hundreds of such papers out there, one could always argue, and I may be excused for saying this, that so you may find this similar results in, say, a country like, there is a paper, say, from Ethiopia. But one then would argue that what happens in a country with 1.5 billion people and these impacts is perhaps more consequential. I don't know, but I'll say that with a bit of a caveat. So the idea is that the downscaling essentially is that you have these grids, but the gridded data has to be converted into some administratively meaningful unit, which for our purposes right now is districts. There are other people who go away from this and just look at remote sensing data. You can get remote sensing data on yields, on, you know, climate, and then just do a globally gridded analysis. And those are the kinds of, there's a very recent paper, I think, in Nature, where they use millions of this, but that's another way to think about it.
Just to add on the gridded work, what we do is, if you look at districts, it's around like 70 kilometers on an average. That's the sort of distance you'll see. And 1 degree would be like around 110 kilometers. 0.5 would be like around 25 kilometers. So you'll see like a lot of missing dots. So typically you'll do something like a bilinear interpolation and plug the gap. That is, I think it maintains the statistical qualities of the estimates that you are trying to do. But for more careful analysis, that may not work. So that's at least what we see in our work. That's the
You mean in the gridded data?
In the gridded data.
Yeah, because remember the gridded data of IMD comes from station level data.
Yeah.
So first the station level data is converted into a grid by the inverse weighting methods, etc. Now from that gridded data, we then use the shape files to convert it into district boundaries, which themselves are changing. Now, people have done different things. So instead of gridded data of this, you have the Aphrodite and so on, where you can have, so there are many different ways, and assumingly the IMD people are professionals, they are trying to do as good a job, but that's not the only data set. The IMD gridded data set, there are a bunch of others.
A lot of reanalysis from the remote sensing data.
Exactly.
That's much higher and higher resolution.
Yeah. So if you want to paraphrase, we have used official data of the agriculture and this and tried to look at this. But I must also say that the results are fairly robust. I mean, if you were trying to do reanalysis and do this, there's so many different directions in which this literature has gone. There is one work which has looked at the synergy between air pollution and climate. So there's a paper which says, okay, it's not just it's climate, but it's also the air pollution that will impact wheat yields. So they've looked at one crop. So again, there are all these, trade-offs, and you have to essentially convince the referees that your work is. So I think our contribution is looking at the comprehensiveness of it in terms of all crops and the longest slice that we can get, and then the three things I've already mentioned: the intra-year variability, the asymmetry, and the dynamic specification.
No, I have a question on if it's okay, I can. Thank you. Very interesting on the persistence effect. It seems like rice and wheat is like very high, whereas something like the millet and your groundnut seems to be the lowest.
The shock is immediately realized.
So is there any follow-up work on the underlying sort of mechanism? Is it the groundwater hydrology, something to do with
a very good question.
Biology,
we haven't looked at that.
Biology of the
We should. Because these are all your alphas, which are then, it's recursive.
Yes.
So it's a summation of the alphas. So the idea is that, so it's a very good question as to Why are we getting some of the shocks are persisting and some of the shocks are just like bang,
Right.
and then it's gone, right?
And maybe the underlying mechanism, or it could even be the the cropping pattern, which is that could also have an impact on this persistence.
Absolutely.
So which will have like immediate policy relevance, whether it's an MSP is the right thing to do, or maybe you want to give some advice on the crop cycles.
So a
and all
deep
that.
dive into this.
Yeah.
Yeah.
Just on that, I think
Namrata, you can take this. Huh?
your temperature impacts were much stronger. The patterns were starker compared to rainfall. And that kind of goes back to, groundwater hydrology or just generally, whether something about being able to mitigate the irrigation shock. Right, so the rainfall, I saw that it was a little bit not as clear as temperature. So is a potential mechanism that somehow we have figured out how to fix the irrigation problem, even in light of all of these changes that are happening. Of course, price-related policy and other mechanisms are always there. But the absolute requirements of agriculture, if those are fixed, then a lot of these shocks can be somehow mitigated. If we could go back to your early, because there were too many results. But
Sorry,
I remember,
I
your
apologize.
early.
They're actually way more. You haven't
the
seen
temperature.
we have
The temperature is very persistent. But
You're talking about
rainfall,
which one?
The first set of main
These are
results
the
that you were
seasonal.
showing.
You look at the annual model, right?
Yeah, the annual model.
And these are the ratios. So you're talking about these. These are the anomalies, right?
Yeah. So if you see for rainfall,
I could show. Maybe it's easier to see the chart, right? So if you can see this one, right? These are the rainfall anomalies, right? Yeah. So what you are telling me is that the
so if you see the rainfall pattern is not as even the long run positive shock.
So here one kind of intuitive explanation for rice, if you buy it, is rice is a water loving crop. So a little bit more rain doesn't do it too much harm, but too little rain is bad for it. So these are the shock too much or too.
But it's also positive. Is what I'm saying.
Where?
Somewhere there is.
So this is telling you it's not significantly. So basically.
So for wheat, for instance, the coefficients are positive.
For wheat, yes. For wheat, you do see these two coefficients as being positive, but for the most part, the coefficients are negative and significant. It's just that because of this asymmetry, and if you really want to focus on these headline crops, what one would argue is that positive rainfall shocks do not matter to rice yields, but negative rainfall shocks do. Over here, yes, this is positive and significant, which is a rainfall shock. And again, you're right that some amount of interaction. So, one way to do this is not look at all 10 crops, but look at wheat or separately, and then just try to understand, maybe bring in the irrigation part and do it that way. So we were struggling with that. So again, we could then, because then you can have, these are like yield functions. So what you're putting in on the right hand side, you could try and bring in, and so earlier work, what I did was I introduced some controls. So we only looked at pearl millet, sorghum and rice, and as controls, in addition to these variables, we had the area under irrigation, the HYVs, the proportion under HYV, and the amount of fertilizer used. And those, as you can imagine, were highly significant. But having said that, you still found the same impacts. But that was an earlier old study where it was a static model and so on and so forth. So I think if you were to customize this, I would definitely try to think about irrigation, but particularly for this crop. But I would argue that barring that, so it's very clear here, when you're looking at these bars, you can see that, and you always see the long run values, which are on the right, to be higher than the short run value. So that point I think I've already made, and you would see that in most cases, the effects are negative and significant. So that was I think we were looking at, So anyway, that's the point.
Professor, I have a clarificatory question. How did you define this beta naught and plus beta 1, that is the coefficient of the lagged climate shock plus the contemporary climate shock, as a short-term impact? Especially there should be a collinearity between the beta naught and beta 1. There is a relation between always.
No, see, we are using instruments, I mean, that's more technical, but we're using lags as instruments. And basically, what I'm really trying to show you is that beta naught plus beta 1, which is the current shock and the last year's shock, those are really what we're calling the short run, because it's an AD11 model. So it's a one period anomaly lag and a 1 period yield lag. You can have, of course, AD1, whatever. So we have identified the ideal lag length using the standard, the error correction mechanism and also testing for this. So that was in the slides there, but I zipped through that. But beta naught plus beta 1 in our analysis captures the short run impacts, or gamma naught plus gamma 1. But there are 4 of them. There's a positive and a negative.
Rho 0.1 is arbitrary, which defines whether it is a positive or if...
We've tried various cutoffs. So we tried a no cutoff, and we also tried a 0.2 cutoff, because otherwise also what happens is that you will have all these numbers floating around. So by having a 0.1 threshold, it's a threshold. What happens is that you don't have to deal with that many anomalies. Those are quote unquote normal years. And intuitively, that's what happens. So for example, if you look at monsoon, and the Indian monsoon, is Indian monsoon normal? It's considered normal, if I'm correctly, within plus minus 5% of the long period average. So it's not that every time the monsoon is a little bit above and a little bit below, you'll call it deficient. So there are these formal definitions that it's a normal monsoon within a band, otherwise it's deficient, otherwise it's a drought. So motivating ourselves by that, we use this 0.1. But the results are robust if you get rid of the threshold. In fact, somebody suggested to us that don't even use the threshold, just model it.
So it isn't clear as to why...
No,
Yeah, so as I mentioned that we did a robustness check, and there is a very long appendix to the paper. We have tried a bunch of different things.
So quick observation on that point itself. If you just look at the definition of rho, it is long-term mean minus x by the sigma, which is actually a z score.
Yeah, it's a standardized...
It's a z, yeah.
It is not one standard deviation interpretation.
Ha.
It's actually 0.1.
Right.
Yeah.
So
Why 0.1 standard deviation? Why not just go with one standard deviation?
No, if it's a z-score distribution, which means that by fixing the, you have a probability interpretation there. Basically it's the z-score.
Sure.
It's a standardized.
From a point of view of interpretation, yes, but the choice of why is
So
0.1.
So 0.1 seems too low.
Too low, yeah. It is too low.
Yeah, because if you have a wider bar, then lots of years will just not be shocks. They'll be normal. So we said, okay, 0 or 0.2, it doesn't matter. Then you could argue, then why just have the threshold? And that's a valid question. But if you don't have the threshold, then lots of more noise will be there. So it's a kind of a judgment call, if you will, but point well taken. I mean, in the appendix, if I remember correctly, my hard-working co-authors, while I'm here giving this talk, are actually doing the work. They have looked at all of this. Yes, Namrata.
So just again, sorry, on this note, which is why I think now climate econometrics is moving away from using even a z-score distribution, because you tend to peg it around some kind of cutoff. Instead, they exploit the entire distribution. Right? So what you do is not just take a standardized value around either a positive or a negative. You just let the distribution speak for itself, and you maybe use, say, number of hot days within a certain temperature bin, and you use that entire. So it could be at the lower end of the distribution, that the number of days in this temperature bin is n.
Yeah, the GDD.
Over a certain, yeah. So I think they're trying to get around this problem of arbitrary, whatever, choice of some.
Yeah, look, but I would
let the data of the temperature or whatever is the climate variable speak for itself. Just exploit the entire distribution.
I would push back on that a bit, that yes, I mean the threshold can be abandoned. But the idea is that the GDD is a very different animal. Firstly, the GDD, the growing degree days, the cumulative heat input, or the killer degree days, is when you have much better seasonal data. I mean, so this is the period in which rice is growing, and this is when it's being exposed to the heat. So the GDD is used in that data where it's my understanding that you have more seasonal kind of variability. Yeah, you could use GDD, but I don't think that the GDD also firstly, you will have different GDDs because the heat thresholds for different crops are different. So when you do GDDs, you're usually only looking at a wheat or a soybean, and a lot of this has been done in the US and of course India also they have done GDDs. The Gutierrez paper, which is an old one, does it. So I would say, but I think the basic pitch that we are making here is about the nonlinearity and asymmetric, that it's not simply how many hot days and cold days you had, but how they are actually figuring into it. So there's another paper which simply looks at this by Zaveri at the World Bank. It's I think in ERL or one of those, which she looks at the standard deviation within a year. Was this year more variable? That sort of idea.
One of the papers you cited was Somanathan. So Somanathan's own work also, I think now they have started using the GDD type of temperature.
Som's paper is actually, that Gupta, that's not me. That was what he did in that was he only looked at wheat yields, the climatic change paper, and what they did, he and his co-authors, is they looked at a kind of this, not just temperature, but also air pollution. I think it was ozone or something. But their data was much smaller because obviously when you're looking at air quality, you're not going to get this kind of sweep. So there are all these trade-offs, but point well taken, and I'm not quite sure, but we can try the GDDs. But right now we are sort of thinking about, we are more thinking about these anomalies and how these are behaving, and we also are trying to justify this by thinking of how climatologists are thinking about climate change. There's a change in the climate, which is a change from the normal. You can, of course, there are limitations because, short bursts of heavy rainfall, so that's very wet days, very hot days. Those are alternative ways of thinking about it, and probably.
I just have a question for my understanding. So you have convincingly showed that the long-term effects are much more pronounced. For example, in one of the slides, you show that the impact on wheat was thought to be 2 to 4%, and now in your study it's 19%, right?
Yeah.
So in terms of how we have thought about adaptation so far, does it then imply that we have only thought of adaptation with half the picture in mind? And if these results are true, then we need to overhaul the way we are thinking about adaptation. We are much more worse off than we have thought we are as of now.
So this is all historical data. So what we are saying is that if you really think about this problem the way we are suggesting, then the impact so far have been underestimated. That's what we are saying. So say for example in wheat, these are orders of magnitude. So the idea is that if you were to just use the static model, you would be missing, the impacts are much worse. But this is sort of backward looking. Now what happens in the future depends not only on projections, but also how you model the adaptation in future. It's not simply that it's going to happen and you're going to not do anything about it. But that's a much harder question, and I must confess we don't have our heads wrapped around it, but the idea is that the literature, which is looking at projections, is also more or less taking these coefficients and then just putting in the future temperature, etc., and then telling you this is what's going to happen. So the adaptation part is not fully worked. And here it is, because it's all reduced form. This is the data that you have. So if the farmers have reallocated crops, done whatever, it all shows up in the yield, right? And the lagged yields.
Hi, Professor. So in the future projections that you showed with RCP 4.5, I noticed that most of the districts were coastal districts. And I think it would be interesting to think about how coastal flooding and sea level rise influence, rice particularly as well. Because I noticed that a lot of the districts in Kerala are, they have Pokali rice farming where it's not just about rainfall and temperature, but also tidal flooding impact as well. So that could be an additional thing that can be discussed. And another thing I wanted to also mention is that we have, you've added district fixed effects and time fixed effects, but is it also useful to think about extreme weather events as, there are districts which are cyclone prone, where you kind of hear all the time that there was a cyclone and a lot of crops were affected. So if you have, it would be, district, it would vary over time. And that could be an additional thing to control when it comes to extreme weather events and how that influences crop yields as well? Thank you.
So econometrically, you would not have a district fixed effect picking it up. You'll have a...
Neither would a time fixed effect, because not all districts are going to have
You would
that.
need, I'm trying to think, you would, like for example, you can have a
So for example,
state time or something like an interactive.
yes.
There are these interactive. So
Yeah.
when we are doing a regional model, which I haven't presented, the regional model wasn't doing that well. And I was just yesterday, I suggested to my co-authors that we should use a region time
Yeah.
interaction.
Exactly.
So yeah, this is a standard two-way fixed effect, but I think I should be writing all this down. So no, thank you. For the coastal, yes, we could think of flooding and those. We'll need the data for future sea level rise or something to model that. Of course, one sort of a cop-out answer is a lot of the stuff that we're growing is now in Punjab, etc., right? But they may be subject to some other kind of negative shock, which is not just being measured by all this. I think we are going to be limited simply by how good the data we are going to get. And when it comes to hurricanes, I mean cyclones and all, I'm just loud thinking we have some Poisson process to model the arrival and then see what's going to happen.
Yeah, and there is IMD data as well, which identifies which are the districts where a cyclone alert has been issued.
Okay.
So that would also be something that can be used.
But it will basically be a time-varying district effect, right?
Yeah, yeah.
So they need to have that sort of
Yes.
thing. Okay, that's a good point. Yeah, yeah. Okay, so when we do our projections, we'll keep that in mind.
Yeah,
By the way, those maps, just forget, because those are being redone, you know. We only had mid 2030 and 2050, so we interpolated, and then we finally went after the numbers, and we got those. So we have to now redo the entire thing. But I think the projections are important, you know, because that makes it more meaningful and also more publishable, I guess.
Yeah, sir, for the main specification, can we use aggregated lagged value of a preceding season crop? For example, there are winter crop, summer crop, and monsoon crop. So for if we are estimating for a rise in time period T, so can we use aggregated of, let's say, winter crops, all winter crops combined, which can account for, let's say, fertilizer use in the preceding season?
You mean revenue?
No, yields.
Yields.
Lagged value. So
We don't have the seasonal data.
No. We have annual data. So let's say wheat is a winter crop, rice is a summer crop, mainly in northern parts. So when we are doing for rice, we are using lagged value of rice plus lagged value of wheat and other winter crops. So can't it
No, here the lag is only of that crop. It's not of other crops. So it's crop C.
Yes.
So the YICT -1 is the lagged value of that crop. We are not mixing it up. There's a very different literature which aggregates the agricultural output. So it has prices multiplied by output, and that gives you sort of the gross output. You know, it's almost like but you know, there are huge problems there, because that's the Ricardian approach where you can either look at the gross value of output, each crop times its price minus input, and look at the net value and then regress that. Or you can do this other thing, but you know, then you're using prices, and what are the real prices? Are these farm gate prices? Are these retail prices? We don't know. There are older papers do that. Newer papers, so here we are just doing crop specific yield functions, like a production function. That's all we are doing. And yeah, I mean, if wheat is only a single season crop, then all that is telling you is that that annual data has just become C. So that's why seasonal model becomes important. Then our growing season dummies, not the dummies, the shocks are going to be important, and the other seasons are not going to matter. So in that way, we can parse it out. So instead of using one annual rainfall shock, we have now in the seasonal model. And as I've already told you that we have rejected the null that seasonal parameters are equal. So it is telling us to use a seasonal model. And presumably that is going to pick up for some crops. But rice, for example, is ubiquitous, and it's grown in many parts of the country as a single crop, double crop. maybe 3 crops in some parts of Bengal, we don't know. So rice is all over the map. Some crops are single season, but hopefully the data is reflecting that rather than something else.
Okay, thank you very much. I think we have to end here. Thanks a lot, Shreekant, for an engaging conversation. I hope you enjoyed it as much as I did, at least. Thanks, everyone. And we have the Professor Saravanan. We request him to give a small token of appreciation from the center and from the institute.
Thank you. Thank you. It's lovely. Very nice. Thank you.
Thank you.